Welcome to Espresso and Electronics, quick sips of EDO wisdom. I'm your host Anika Sunda, and joining me today is Amit Dua, Senior Group Director at Cadence Design Systems. Amit brings over 3 decades of experience, and he brings a lot of skills to the table, right from product development to product engineering. Amit is leading the worldwide product engineering team at Cadence. Welcome to the show, Amit.
Thank you, Anika. Thanks for having me.
So today's topic is very special because I think a lot of DV engineers will connect to this. The topic that we're going to discuss today with Amit is how to achieve first pass silicon success with confidence. So Amit, let's start with something I want everyone to sit with for a moment. In 2024, we saw the lowest first silicon success rate in 2 decades. And this has happened even when we have more verification tools, we have more compute, we have more AI assistants than at any point in history. But I believe that the number is moving in the wrong direction. So Amit, can you share one of the key reasons why many chips are not working correctly at the first time when they come back from fab?
Sure. Yeah, it's a very good question, Anika. As we all know, it's a well-known fact that as designs grow in sizes, the verification complexity increases exponentially. With larger designs, what happens is there are more states to be verified, more interactions between them, and as a result, doing the exhaustive coverage with simulation becomes a very hard problem. Now, yes, you're right. There's more compute now, and with AI coming in, it becomes much faster and better. But still, the biggest challenge today in the chip design is how to do the verification closure without risk of a functional bug in it. So, and more recently, the stakes are even higher because at these advanced nodes, the respins can cost a delay of 6 to 9 months, which can potentially be a cost of tens of millions of dollars.
Yeah.
So that's the challenge. And since you asked about a key reason, I would say one key reason for lesser first silicon success is that RTL simulations cannot cover certain verification cases, especially related to timing. Now, we know there are STA tools which work on the basis of some constraints assumptions, but those still needs to be verified at gate level simulations with full timing. And now we know that gate level simulations with full timing, these are extremely slow. They come very late in the design process.
It's a pain, I'm sure.
And yes, and then and on top of that, when there's a failure, they are very hard to debug at that level of abstraction. So doing GLS timing is still happens, but it is very expensive, very late, and it is very hard to debug. So the challenge, and this results in some of the cases of a bug slipping into silicon. The challenge is not what to verify, but how can we verify them sooner at RTL rather than doing later at GLS timing, which introduces the risk that you talked about.
So are you saying this is like the entire shift left? You're moving everything from the
Yes,
expensive side to the inexpensive side.
Yes, that's the need. The sooner you can, the earlier you can find the bug or you can find your functional issues, ideally at an RTL level, then you are more confident, you have more time to put the fix. So that's exactly is one of the things we want to do.
Of course. Okay, so this is good introduction, Amit. Now let's get down into the details of this class of bugs, right? Because they are probably the ones that look completely innocent in the RTL domain, but they absolutely ruin your day at the gate level, and they're very expensive. I mean, imagine getting a bug closer to your tape out or your silicon is ready. So help me understand why these are so hard to catch early.
Sure. As I said, STA tools are there to ensure that the timing is met based on the given clock frequencies of the design. Now, STA relies on assumptions that the design constraints files are correct, like the constraints specified are honored by the STA tools. So any wrong assumptions there could lead to a silicon bug. There are some specific examples, like there's a multi-cycle path delay that is not accurate, which means it reaches in the real silicon not in the same number of cycles as they are specified as MCP delays. Or there are certain timing paths that are marked false but are exercised, or there are clock groups that are marked incorrectly. So STA tools is going to relax or completely ignore these things specified in the constraint file. So essentially nothing is checked. Now, for those specific reasons, GLST has to be done. They have to confirm that there are no timing issues. These constraints, since they may not be accurate, so they have to run very long gate level timing simulations. There's another issue, which is with glitches. What happens is that there are combinational logic in the MCPs, and these paths can produce glitches. These cannot show up in RTL,
Of course.
as there is no delay. Only GLS is when there are differences in IO path delays. That's when the glitches will come in. But as we said, these could be fatal issues, because if the glitches are in, for example, asynchronous resets, or in some gated clocks, or in CDC paths, then these could lead to a very, the silicon failure kind of bugs. So finding the right bug, this is what is typically called as we find the right bug, but find it at the wrong time.
Yes, exactly.
Right. So the critical issue is it's very hard to catch them early, and for those reasons, it's very difficult to find them at an RTL stage.
Correct. I think we have tools, but then maybe people are not using it at the correct time. It's like when the iron is hot, right? So you have to use the correct thing at the correct point, right?
Yes, that's where what we are trying to solve in the EDA industry. We're trying to give them so that we can do this shift left, as you said, so that we can find these issues at RTL level rather than waiting for a much later and more expensive gate level simulations.
Of course. Okay, so Amit, since you've worn a lot of hats, you bring a lot of skills to the table. If a team recognizes these problems on their project, right, what is your recommendation, or how do you think they can overcome them, right? Are there any solutions that you can tell the audience how to address this challenging problem?
Yes. So since I'll focus on the timing things that we want to verify. As I said, multi-cycle path and false path, these are actually architectural features, which means they must be specified along with the functional intent and should be verified sooner at an RTL level. Now, this is what we call as shift left, which means you verify early at RTL rather than waiting for your gate level. And now, Xcelium simulator has added this capability native into its simulator recently. So what we do is in Xcelium, we support the design constraint-aware simulation natively at RTL. What it means is that the timing constraints like the MCPs, the false path, these are read directly into RTL sims, into the Xcelium simulator. Imagine now this is happening before synthesis. So you can find these kind of issues at your RTL level. What we do, for example, now in each of these cases is in MCP, the tool checks if the timing is already taken care of in RTL, and else if not, then you can annotate some delay. The delay so that it matches the gate level behavior at an RTL level. So you are trying to mimic what you would have seen with delays at those cycles. We are trying to introduce the delay for that many cycles in the multi-cycle paths at an RTL level. Likewise, in false path, if you want to verify whether a path is false, if they get traversed in the simulation, dynamically in a simulation, then the tool can inject corruption. When it injects corruption, the purpose is basically to find out if RTL can handle metastability or non-critical timing paths.
So having said this, there's so much complexity. Do you think the simulator takes a hit on performance, or do you think it is?
So yes, there is an extra instrumentation both at the build time and at runtime, but usually the cost, if you imagine what you have to do at doing at the gate level and the amount of shift left that is happening, yes, if you compare it with your regular RTL sims, there will be an overhead, but the productivity and the benefit that you are going to get with this is going to be extremely high. And as I said, you are finding it months before you would have otherwise found.
So it means it is in the limit that somebody can digest. So within the...
Yes, definitely.
Got it.
And then there are other things like CDC, where tool can inject metastability on the first synchronizer. So those kind of issues, these can be done now at RTL level. So that's on what you see in your constraint sides. Then, as I talked about glitch,
right.
What we can also do is for doing your glitch verification at RTL level, we can, for a given target, we can identify a combo logic in the fan-in cone of the target, and then we can inject the glitches if there are multiple inputs that are changing in the fan-in cone. So that helps you to give you glitches. Also, to simulate with glitches at an RTL level, which otherwise, as I said, would only happen when you have IO part delays coming in later in the gate level simulations. And if you're wondering how we are doing this, this is...
My next question was, which app are you asking us to use for these?
Sure. So we have Xcelium simulator has provides any specific verification task through Xcelium apps. So we have for the timing constraint verification app, or the TCV app in Xcelium, and for glitch we simply call it a glitch verification app.
Okay.
And the good part is this is, as you talked about the performance, we have a patented active path tracing algorithm which makes it accurate. And unlike traditional simulator, which only had the concepts of events and nodes, because of this technology, we are able to have the notion of path in simulation. So which makes it very powerful and makes it very accurate to find these issues at RTL. So yeah, overall it's much faster, it's much earlier, and it's easier to debug as well.
Yeah, of course. So I think, yeah, the debug and the simulation go hand in hand, right?
Yep.
So I'm pretty sure.
Yes.
Okay. Thank you, Amit. It was a pleasure having you on the show.
You're welcome.
Thank you, listeners, for tuning in. Keep your circuits connected and your ideas flowing until we meet next on Espresso and Electronics.